Today's lesson, we're going to review radicals. We're going to remember how to simplify them. We're going to remember how to combine them. And then we're also going to remember how to rationalize on them as well. When you're working with radicals, the general rule here is that you want to be careful with your factoring. And I say that you want to factor strategically, keeping the index in mind. And I'll show you what I mean as we run through these problems. Looking at example 1, combine and or simplify expression. So I have 2 on the square roots of 48 minus 3 on the square roots of 27. Well, let's write off to the side here some factorizations for 48. So this is what I was saying a second ago with factoring strategically. Well, 48, one factorization for 48 would be 2 and 24. Another factorization would be 3 and 16, 4 and 12. Let's see, do I have any more? Oh yeah, 6 and 8. So the question is, which one do I want to use? Because any one of those will produce a product of 48. Well, the answer is I want to use 3 and 16. And the reason why I want that version is because 16 is the largest perfect square factorization of 48. So I have 2 on the square roots of 16 times 3. And then the 16 is a perfect square, and so that's going to come out, and when it comes out as a 4. So then I have 4 times 2 on the square root of 3, and of course 4 times 2 is 8. Well, 27 is a little bit easier to work with because 27, there's fewer factors, and 9 times 3 is probably the one that most people think of right away besides, 27 and 1. And so 9 is a perfect square. So I have minus 3 on the square roots of 9 times 3. And again, the perfect square comes out. So the square roots of 9, that's going to come out. And of course, that's going to be 3. And 3 times itself is 9. And then when I add those together, I get negative 1 on root 3. When you combine radicals, you can add and subtract on them if they are like terms. So what makes them a like term is, I call these coefficients. These need to be the same. If they're integers, that's fine. If they have variables on them, the variables have to be identical in order to add or subtract them. In addition, the index must be the same. In this case, it's a square root. And the radicand must also be the same. If that is all true, then you can add or subtract the terms because they are like terms. Number 2, notice that I have an index of 3. So this time I'm taking the cubed roots of 250x minus the cubed roots of 54x. Well, 250, just like I did on the last one, 250, you can factor that numerous ways, and a lot of people want to use 25 and 10 for that. But see, 25 is not a perfect cube. My index in this one is a cube, and so I need to come up with a factorization that has a perfect cube in it, and 125 is a perfect cube. So when I revise 250, I'm going to revise that as 125 times 2, don't lose the x, because 125 is now a perfect cube and that can come out. So the cubed roots of 125 is 5. So this simplifies to 5 on the cubed roots of 2x. And then I also want to work 54. Well, 54, the best factorization is going to be 27 and 2. And again, the reason I'm choosing 27 is because 27 is a perfect cube. And so that's going to come out, and that's going to come out as a 3. Notice that the term in front, these are both integers, so those are like terms. The indices, it's both a cubed root, and then the radical, or the radicand, is a 2x. Therefore, these are like terms, and we can go ahead and add or subtract the coefficients. So in this case, we have 2 on the cubed roots of 2x. Now, be very careful that you put that 3 on there, because if you don't put the 3 on there, you're telling me that you're doing a square root, and there are other roots besides square roots, and that's going to be an incorrect answer. So just don't overlook that. All right, number 3, I've got the cubed roots of 54z minus 2 on the cubed roots of 40z plus the cubed roots of 2z. Well, this first one, this is, the same value, the 54, so we already went through that one. So that's going to simplify to 3 on the cubed roots of 2z. Okay, now let's go ahead and do the next term. So I'm going to have to deal with the 40. Well, what's the best factorization for 40? Well, in this case, I want to use 8 and 5 because 8 is a perfect cube. And so, of course, that 8 is going to come out, and the cubed roots of 8 is going to be 2. So that's going to give me -4 on the cubed roots of 5z when I simplify that. My last term, there's nothing that I can do with that one, so I'm going to go ahead and just rewrite it here. And then I'm going to bring down my first one too again. Now, can you add and subtract all of these terms? The answer is no, you can't. This middle term here is on the same index, and the coefficient, that's not the problem. The problem for this one is that the radicand is 5z, whereas the other two radicands are both 2z. Therefore, that term in the middle is not like, and you can't combine them. We can combine the first and the last term, and notice that a 3, and this last term has a coefficient really of 1, but we don't write it down. So that's going to give us a sum of 4. So I've got 4 on the cubed roots of 2z minus 4 on the cubed roots of 5z. And this would be your final answer. You can't take that any further. And again, that's because the radicands are not the same. Therefore, they are not like terms. The next skill we want to refresh ourselves on is how we rationalize. So we're going to rewrite each expression by rationalizing the denominator, and then we're going to simplify. When we simplify, we are not going to use decimals. Or square roots in the denominator when we're done. So the procedure of rationalizing means to eliminate the radicals, in this case in the denominator. What I have to do is I have to think in my mind, what do I multiply by to turn this number, the radicand, turn that into a perfect square? Well, this one's pretty easy. I just need to introduce the square roots of 2. So then I'd have in the numerator 6 root 2, and then my denominator would be 5 times the square root of 4. Well, of course, the square roots of 4 is 2. So then I have 6 square roots of 2 divided by 10. And the 6 and the 10 can both be reduced because they're outside of the radicals. And those would both reduce by 2. And that's going to give me my final answer then. So my final answer here is going to be 3 on the square roots of 2 divided by 5. Looking at number 2, I've got 7 divided by the square roots of 32. Well, 32 you can rationalize square roots of 32, but if you choose to do that, you're just going to end up making a bigger number that you're going to have to reduce. And so in my opinion, I think it's best to simplify that a little bit if you can before you do the rationalizing step. Okay, 32, we would want to use 16 and 2 for that. And of course, 16 is my perfect square factor, so that's going to come out. So notice then that I have 7 divided by 4 on the square roots of 2. Well, now my rationalizing step is just like what I had before. I'm going to multiply by root 2 and root 2. So that's going to give me 7 root 2 divided by 4 on the square roots of 4. And again, square roots of 4 is 2. And so I'm going to have a final answer then of 7 square roots of 2 divided by 8. And again, just make sure the 7 and the 8 here, those are both outside the radical, but of course those can't be reduced. So that is my final answer. Looking at number 3. Now number 3 is a little bit different because now in my denominator I have a difference. Recall that when you have a sum or difference and you are rationalizing, we introduce the conjugate. And the conjugate is just the same expression, but it's opposite in sign. Now, the whole reason the conjugate is helpful is because this is one of my special patterns, and this will eliminate the root. So look at what happens. I'm going to just write this off to the side for a minute. So notice that I have root 5 minus 3, and then I have root 5 plus 3. Well, my special pattern, remember, if you have a minus b times a plus b, that's going to give you a squared minus b squared. That's that difference of two squares pattern. So back to my problem, that's going to give me root 5 quantity squared minus 3 squared. Now the numerator, be careful because you have to use the distributive property and you have to distribute that 12 onto each term of the sum. So I'm going to have 12 on the square roots of 5 plus 36. Now my denominator, notice that the square roots of 5 squared, that's just going to cancel out, so you get 5. And then 3 squared, of course, is 9. So now I have 12 root 5 plus 36 divided by negative 4. Well, that's going to simplify, and you can write it as two separate fractions if you want. And if you can see this in your mind, that's okay too. So if I separated that into two separate fractions, notice that I have 12 root 5 over negative 4, and then plus 36 over negative 4. Well, again, any term that's not inside the root, I can simplify on that. So my first term would be negative 3 root 5, and then my second fraction, of course, reduces to negative 9. So that's my final answer for this one. And you do need to simplify that whenever you can reduce those fractions. All right, number 4 is basically the same problem. So again, to eliminate that radical, we're going to introduce the conjugate. And that's going to be 2 minus root 5. Okay, and remember that that numerator, that's going to be a distributive property pattern. So I have 12 minus 6 root 5. And then my denominator is that special pattern, the difference of two squares. And so that's going to give me 2 squared minus root 5 squared. And when I simplify that, 2 squared, of course, is 4. Root 5 quantity squared is 5. And so notice that my denominator is simply negative 1. So I have 12 minus 6 root 5 over negative 1. And again, we need to simplify that. So I would want your final answer to be negative 12 plus 6 on the square roots of 5. And some students ask, should I write the radical as the first term or should I leave it as the second term? And for me, it doesn't matter. So either one would be fine. All right, now looking at example 5. So example 5 here is a little bit more complicated because we have 2 radicals on this one. Well, the conjugate for this one is going to be 2 root 5 plus root 3. And the simplifying, you just have to be a little bit more careful here with your algebra. So my numerator, again, I'm still got a distributive property here, so I have to take that 5 and multiply it with each term. And so that's going to give me 10 square root 5 plus 5 square roots of 3. And then my denominator, now here's kind of the tricky part. You've got to do quantity 2 root 5 because that's your a. You have to square that and then also square your root 3. Now you have to apply your exponent rule. So you have a 2 factor and a root 5 factor, and these are both being squared. So that means that that exponent has to get applied to each factor. In doing so, we will get 4 times 5, and then of course that second term is just 3. And then my denominator, 20 minus 3 is 17. And that's not going to simplify any further, so that's going to be my final answer. So my final answer here is going to be 10 root 5 plus 5 root 3 all over 17. And I would prefer it together like that versus 2 separate terms. All right, that's going to conclude day 1 for radicals. Hopefully you're kind of remembering, how all these rules work. And we will add on to our radical skills tomorrow. Good luck with your assignment.